Hey guys, today we're going to be looking at diffraction patterns and interference for light waves. First up is the definition of diffraction. Diffraction is defined as the spreading of a wave to fill the area behind a gap. So you can see here, I've got two different pictures. The first one shows a simulation of water waves, okay? And you can see where the wavefronts are straight right here. They spread out over here to fill that area behind the gap. They don't just keep going straight down the page the direction they were. They curve and spread out. And the same thing happens for light. As it goes through tiny little gap here, it spreads out to fill all of that area behind the gap. And that's what we call diffraction. All right, but there is a condition for diffraction. The condition is that waves will only diffract through openings that are similar in size to their wavelength or longer. So if you've got a giant opening like this is your opening. Say we'll make it a doorway. If you've got tiny little wave, little baby wave here with tiny little wavelength, it's not going to diffract through that opening. But if you've got big wave, it can diffract through that opening, because its wavelength is similar in size to the gap, or the wavelength is longer. And this is why you can't see around corners, but you can hear around corners, because the waves will diffract. Because the wavelengths for light are very, very small. They're like 400 to 700 nanometers. But the wavelengths for sound range anywhere from 17 millimeters, which is still pretty small, to 17 meters, which is huge. So through doorways and hallways and around corners, the sound waves can diffract because their wavelength is long enough. The light waves will not. All right, this next little part of the lecture actually comes from a PhET simulation, which I can't run in this program. So I'm going to leave it up to you. If you go to the Google Classroom slides, to the slide that says interference, and click on the simulation, you'll see some waveform patterns. Basically, it's saying that if you got two waves in the same space, one wave, say it's like this, one wave, say it's also like that. If that's two waves in the same space, they add up and make one total wave that is very large and then very small. Well, not small, but it's got a very low trough there. So you add those two waves together. Alternatively, let's see if I can erase this stuff. I can. Alternatively, if you've got one wave that looks like this and another wave that is opposite of that in the same space, and you add them together, you just get a flat line there. Your crests and your troughs, where they exactly line up, they cancel each other out and just leave a flat line in their place. That's basically interference. You can go mess with it in the simulation. If you haven't seen it before, I recommend you do that, because we're going to be using the idea heavily today. Okay, so the actual experiment we're looking at today is called Young's double slit experiment, which is an experiment that proved that light has a wave-like nature because it does diffract here. And you can see the diffraction based on the pattern on the viewing screen. So what it is a laser that you know the wavelength of, and it's going through two little slits right here. And these are exaggerated for the picture. In reality, they're very, very small. They got to be on the order of nanometers. That way light will diffract through them. So what you get is two different sources of light, one through each slit. And they diffract after they go through the gap. And when they diffract, they spread out like you see here. So like the left slit gap thing is making this spread, and the right one is making that spread. But here in this middle region, they actually overlap. And that overlapping causes some interference. The waveforms will add together. And where they add together constructively, meaning they build each other up and make a larger waveform, you see bright sections of light. Where they destructively interfere and completely cancel each other out, you see dark bands. And once again, can't run a simulation in this program. So if you go to the slides, click on the slide that says PhET, click on that. you can mess around there with the diffraction patterns, and you can see the constructive and destructive interference and how it works. That's what we did in class. I recommend you go do that. So here's a side view, or not really side view, I guess a top view of what's happening. You've got light going through your two little gaps, and it is arcing out after that. It is diffracting, and you're going to have light hitting a screen over here from those waves. Now these lines right here, they are tracing one particular ray of light, even though there are rays spreading out everywhere. So each line here is tracing one specific ray going to a specific point. Up here, we're looking at this point right here, okay, where there is a bright fringe. These little sections where it's light or dark, they're called fringes. So at this one point right here, we know that they must be constructively interfering because they're building each other up and creating more light. But a different point, say this point here, they would be destructively interfering or canceling each other out so you don't get any light right there on that screen. And these different points where it is light or dark are called fringes, and they have a very specific numbering system. So the middle bright fringe, the one right in the very center, which is right here, this one, that is the 0th fringe. Okay, it's m equals 0. M is the integer number for the fringes. And going out from there, you move up by 1. 1, 2, 3, 4, so on and so forth. You could have infinite number of fringes. But as you go down, it's also 1, 2, 3, 4. It's just symmetrical going up and down. So the first fringe could either be this one or this one. Doesn't really matter either way. And then the dark fringes are numbered where this would be the first one, and this would be the second, third, fourth, so on and so forth out from the middle. There is no 0th dark fringe. But when you say the third dark fringe, that does not have an m equals 3. That m is going to be a different number. We'll see here in a minute. So the job that goes with Young's double slit experiment is being able to calculate the spacing of the fringes, or the angle to get to the fringe, or how far away a certain fringe is. Basically, you just need to be able to locate those fringes on the screen. And you do that with these two equations. Now I'm going to be straight up with you guys. This top equation, kind of dumb, not helpful. It says that the change in path length equals m, which is an integer, times the wavelength of the light. This L, we said, is change in path length. So the path length is how far a ray travels to get to a certain point. So if you've got your two slits right there and a viewing screen, light coming from one slit will have a certain distance, and light coming from the other slit will have a different distance, L2. So this change in path length is the difference between your L1 and your L2. The thing is, you're not actually going to be calculating that distance, so this equation is kind of useless. What you do need to know, and will use a lot, is this equation. D sine theta equals m times lambda. D here is distance between the gaps or the slits. Distance between slits, which is like this little doodad right there. Tiny little d. It's going to be very, very, very small. And that's multiplied by the sine of theta. Your theta is going to be the angle between the perpendicular line right in the middle of the slits to that point. This is your theta. Sorry, that's a poorly drawn picture. And then m is just a number. It's the number of the fringe you're looking for. So you could be looking for the first fringe, the 12th fringe, the 30th fringe, whichever one. You put that number there for bright fringes. That's for bright fringes. If it's a dark fringe, you have to go up by a half because those are halfway in between the bright fringes. So if you're looking for, say, the 18th dark fringe, you'd have to go to the 18th regular fringe, and actually you would scoot back by a half, right? Because if you've got a light in the middle, that's the 0th, and then this is the first and the second, or the first two bright ones, like this is M equals 0 and M equals 1, M equals 1. The dark fringes would be at half, 3/2, whatever. So you would go to your bright fringe number M, subtract a half, and that would give you your dark fringe. And you just plug that number right in there for M in the equation. And then the lambda is the wavelength of light you're looking at. So red will have a different frequency, different wavelength than blue, which will be different than yellow. All right, then we got these two bad boys right here. These two equations are super non-important because they're only shortcuts for in your homework, so you don't have to do a crazy amount of trig. They're not actually used in AP or on your test, so these will help you out on homework. This y sub m, that tells you the position of the mth bright fringe. And actually, these are approximations, which is gross. And then it equals your M for whatever bright fringe times your wavelength. This L is the distance between slit and screen. So if this is your setup, this distance would be L. And then D is once again the distance between your two slits. This other equation tells you the difference in position, or the distance between two different fringes that are adjacent to each other, and it's the same variables just without the M. So if you need to find the distance between two fringes, or you're given the distance between two fringes, this equation is your best friend. Once again, these are not covered by AP. They're not on your test. They're not on your formula sheet, but they are on your homework. And if you try to do your homework without them, it's going to take you a lot more time and a lot more trig. And the trig is actually going to turn out pretty gross. So use these guys. All right, our example question here says 2 narrow slits 0.04 millimeters apart are illuminated by light from a helium neon laser with lambda 633 nanometers. What is the angle of the first bright fringe? What is the angle of the 30th bright fringe? All right, so our equation is D times sine of theta equals M times lambda. And this is really just plug and play. Your distance is 0.04 millimeters, which you do have to change to meters by moving the decimal 3 times. So you go 0.04, scoot it 1, 2, 3. That's a lot of zeros. That's 0.0004 times sine of theta. Theta here is what we're looking for. So we're leaving it there. Sine theta equals M. For the first fringe, M is 1. Remember, this is not the center fringe. This is one out from the center. The center fringe is 0. I'll multiply that by lambda, which here is 633, but it is nanometers, so you got to do times 10 to the negative 9th. Always need to be in our SI unit. And you solve that for theta. I'm not going to actually go type it into a calculator, but I believe it's like 0.90 something or another in degrees. Now, if you're going to do the angle for the 30th fringe, you just change this M to a 30. So you do 0.0004 sine theta equals 30 times 633 times 10 to the negative 9th. Solve that, and your theta is somewhere around 28 degrees. I don't remember what the rest of the number is there, but something around 28. Okay, and that's all the lecture I have for you guys today. You're just going to be using these equations, applying it to the Young's double slit experiment. If you have questions, please let me know. If you need to set up a If you need to set up a Google Meet, you just email me. We can figure one out. I can only do that during third block because third block is my conference period. So email me and we can get that set up.